So today's presentation is on large sample hydrology. And basically it is on doing hydrology with data from hundreds to thousands of catchments. And the focus really will be on the data sets that enable us to do it. So I am Addor, and Gemma Coxon from the University of Bristol and Frederic Kratzert from Google have contributed to this presentation. Together with Gemma and Frederic, I've contributed to some large data sets for hydrology. And today we thought that we could share our experience with you, on creating these data sets. And while telling you a little bit about how they came together, we also would like to just highlight what data sets are out there and can be used for large sample hydrology. And there are luckily more and more of them. And this presentation is also a way to reflect a little bit, to look back and realize how much progress has been made over the last few years. But it's also an occasion to be critical and to reflect about challenges that we have to overcome as a community. And it's a way to think about how we're going next. So what is motivation? Really, our motivation is to make hydrological relevant data easier to use and publicly available. And when possible, to do it using open methods. And in this process, to create a community of users around these data sets. So really, we're working with data from hundreds to thousands of catchments. And this, by definition, means that we're working with fairly large spatial domains that include a fair amount of hydrologic diversity. And then you might say, well, this means that you do large-scale hydrology. Well, yes and no. There are some key differences there. Our focus is typically on flow, when large-scale hydrology, often we look at flow, but also at other fluxes, for instance, evaporation. And our focus is really very much at the catchment scale, when large-scale hydrology would work with, well, catchment scale, but all the way to continental scale and working with domains that are continuous. Whereas for large hydrology, by working at the catchment scale, it means that the domain is discontinuous. So this is why we refer to this field, as large sample hydrology. And this typically reflects the fact that we're working with the large number of catchments. And clearly it's a field that is evolving quite rapidly, and this is thanks to the many creators and users of our large sample data sets around the world, and I'll try to do them justice today. So the outline of this presentation is as follows. I'll first give you a brief introduction to what large sample hydrology is, where it comes from, and then I'll give you an overview of some regional data sets, like camels, Great Britain, and other data sets. And then I'll talk a little bit about challenges in large sample hydrology and potential ways to overcome them. And this will be the perfect occasion, actually, to introduce you to the project Caravan. So where does large sample hydrology come from? Well, if we go back to this UNESCO report published in 1989 and edited by Falkenbach and Chapman, well, they defined comparative hydrology as the study of hydrological processes as influenced by climate and the nature of the Earth's surface and subsurface. And the goal really is to understand interactions between hydrology and the ecosystem and trying to get a better sense of whether what we observe in a specific location, what you predict at a specific location, can be transferred to another area. And this is very similar to what you try to achieve in large sample hydrology. I think a key milestone in the development of large sample hydrology was the release of a data set called MOPEX. And MOPEX includes data from about 400 catchments across the US. And it's being used very, very widely in hydrology. And I think it's quite interesting to go back to the original paper and to remind ourselves what MOPEX stands for. It stands for Model Parameter Estimation Experiment. And this really tells you that modeling was a key motivation for the release of the MOPEX dataset. The idea, obviously, that hydrologists should work with a large number of basins is not new, and there is a strong recognition that if we want really to test how well models are doing, then we need to test them on as many catchments as possible and test them in catchment with widely different characteristics. And this idea really gained traction in large sample hydrology. And large sample hydrology in itself, as a term, I think was really popularized by this paper published in 2014 by Harshin Gupta and his colleagues. And the claim they make there is that there is a need to balance depth with breadth. And by depth, they mean the very rich information that we can collect in a well-instrumented research catchment that is very varied, very dense, but obviously only characterize the area of the catchment. And these catchments, these well-instrumented catchments, are extremely rare. So the claim there was, well, to actually describe what's happening between these catchments, we can actually use the thousands and thousands of catchments that are instrumented between these catchments, but for which we might not have as much information. We might only, for instance, have flow observation. But this flow information, because it comes from thousands of catchments, can actually be extremely useful. And this paper makes the claim that there are three key goals for large sample hydrology. One is to improve process understanding. The other one is to formulate conclusions that have some statistical significance. Because as you increase the number of catchments, the risk of reporting results that are based on a single catchment that might be an outlier are reduced. So you end up providing actually more robust generalization. And obviously, these data sets are extremely useful for classification, for regionalization, and for model transfer. And this makes common sense. It's fairly intuitive in a way. And in a way, I'm preaching to the choir because I guess many of you are already working with large sample of catchments. But I think it's still useful to look back and actually go back to these papers to gauge how much progress has been made. And this is actually a good example. It's a table that comes from the Gupta et al. Paper 2014 that I just mentioned. And it's a table giving examples of data sets that are potentially useful for large sample hydrology. And roughly speaking, you can actually split this table in two types of categories. You have the sources that give you flow data. And obviously, you'll have GRDC. The Global Runoff Data Center is an absolutely amazing resource when you're looking for flow data because they cover thousands of catchments across the world. The USGS also has a strong open access policy, and so you can get a lot of data from the USGS online. And then there are smaller projects that provide data for parts of the UK or part of France, for instance. So that's the first group of papers, of resources. The other group are more resources that focus on the atmosphere. And so EOPS, for instance, is a data set covering the whole of Europe, for which temperature and precipitation can be retrieved. GWEX is very similar to. Sorry, I keep going. However, what you can see that with the exception of MOPEX, for instance, at the top of the list, in 2014, flow, atmospheric, and landscape attributes were typically in different data sets. What you also see from this list is that many data sets are only available upon request. They're not freely available. And available upon request means that you will have to contact a specific person, a specific institution, but you're not guaranteed that you'll get access to the data. So they're not truly freely available, not truly publicly available. And what you see also from this list that there are fairly large spatial gaps. There is mostly flow from the US, from the UK, Australia, and France, and but not a lot of data for other regions of the world. So this was in 2014, and in 2015, I joined the National Center for Atmospheric Research in Boulder, Colorado. And this is a panorama of the Mesa Lab, the NCAR Mesa Lab, with the beautiful Flatiron Mountains in the background. And at NCAR, I started working on a dataset that would become the CAMELS dataset with Andy Newman in the top left of your screen, Martin Clark, and Naoki Mizukami. And I just want to say briefly that currently my employer is Fathom, and Fathom is a flood modeling company, and we distribute a range of products, but CAMELS and Caravan are not products Fathom is distributing. I'm just presenting them today because I helped with their development. So when I arrived at NCAR, my colleague Andy Newman had already released a data set that brought together data from 671 catchments in the US. And that included daily time series of atmospheric forcing and stream flow observations. And this was for more basins than the MOPEX dataset, with basins that were more equally distributed over the US, longer time series, and more recent data. And the beauty of having a dataset for the US is that it covers a very wide range of hydroclimatic conditions. So this map on the left shows you annual precipitation, and you see that it ranges from a few hundreds of millimeters per year to more than 3 meters of rainfall in some location. And this is a great data set that can be used for many types of study. You can definitely do rainfall runoff modeling just using data from this data set. But if your goal is to gain understanding into catchment behavior, then you need to know more about the catchments. What is the climate like? What is the hydrology like? What is the land cover like? What is the soil like? What is the geology like? And this is what I spend a lot of my time at NCAR doing, and it is to actually collate information from different source data sets to characterize the landscape of these 671 catchments. And at the beginning, it was only meant to be part of the data section of a paper. And I started writing this data section, and when it reached, I don't know, about 15 pages, we thought this is ridiculous. It has to be a standalone paper. And we decided to actually combine these two data sets and create what we called the CAMELS data set. And CAMELS stands for Catchment Attributes and Metrology for Large Sample Studies. And we made the data freely available, and we made the code to compute many of the attributes on GitHub. We even made a logo, and it made many people ask us if we'd received any money from the tobacco industry. And the answer to this is definitely no. But I would say we printed the logo on stickers, and printing stickers is actually a great way for people to get to know the dataset that you've produced. And we didn't exactly know what to expect when we released CAMELS, and it felt it was the right thing to do because we felt that the data could be used by others. And 5 years after the release of the attributes, I think the CAMELS paper has about 300 citations. And we know that the dataset itself has been used in dozens and dozens of studies. And it's been used also in the industry. So way more successful than we expected. And I think what really made the success of CAMELS is this combination of daily time series and catchment attributes. The fact that the data we provided was so easy to use, the fact that it was completely open, I mean, anybody can download the dataset immediately and have access to all the data. And it's all peer-reviewed work. So if you want to know how the data was processed, where it comes from, this is all documented. And I think all this explains its fairly large adoption. What's quite important to stress here is that so for the attributes, we focused on climate, hydrology, characteristic, land cover, and geology. But for each of these datasets, I had to actually download the source dataset. And for instance, for the geology, it's a global dataset. So I downloaded the whole global dataset and then processed it, aggregated the data at the catchment scale. And this is a fairly time-demanding process. And I'll talk in a minute about how we can actually do the same job, but much quicker. Interestingly, as I was working on CAMELS US, other people were working on similar datasets. And this is work that has been led by Gemma Coxon at the University of Bristol. And I met Gemma before CAMELS US was released. And Gemma, during a large part of her PhD and part of her postdoc, had been gathering data for Great Britain. And a few years later, after CAMELS US was published, she published CAMELS GB, which is very similar to CAMELS US in the sense that it's exactly the same number of catchments, so 671. But this is completely by chance. We still don't understand how it happened, but it did happen. And for each of the catchments, we provide hydrological time series and catchment attributes. And the code that was used for CAMELS US was used to a great extent to compute attributes that were provided as part of CAMELS Great Britain. So this actually guarantees some level of comparability between the two datasets. What is quite different is that Gemma managed to retrieve data and that quantify water abstractions, effluent discharges, and reservoir capacity for catchments across England. And this is extremely useful because it enables us to assess the impact of human activities on flow, on hydrology, and that's the first time that this data have been made publicly available. And I briefly would like to mention this study by John Bloomfield at BGS. And we could show actually combining the climate and landscape attributes and the indices characterizing human influence that water resources management practices affect base flow, right? You need to account for these practices if you want to predict and understand base flow, which is usually important, has a wide range of consequences, including on ecosystems. And so this CAMELS dataset paves the way for new data sets and catalyze the release of new data. So there is now a few CAMELS data sets, one for Chile on your left. The flow data for Chile became publicly available for the first time through CAMELS Chile. So that's was really a massive achievement. Data for Australia and CAMELS Brazil. And there are other CAMELS datasets that are being produced for France, Switzerland, and Germany. And again, because these different datasets rely on the same philosophy, they're fairly complementary and comparable, but there are key differences. For instance, in CAMELS US, we don't quantify human influence, but in CAMELS GB, yes, these influences are quantified. We also, a key decision that was made when creating this CAMELS dataset was to use the best possible data, and typically it's meant using national datasets. But obviously, national datasets only cover the country they come from, and they cannot be used to derive parameters or attributes in other countries. And for the US, for instance, we use a solid dataset that is only covered the US. And the key issue is that when we're dealing with qualitative variables like soil type or land cover type, it's really, really difficult to compare data sets because there is no one-to-one comparison for these qualitative variables. Unlike for quantitative variables, if you have precipitation, where the precipitation data comes from doesn't matter a whole lot if you know exactly how much rainfall there is, but for qualitative attributes, it's actually quite difficult to compare data sets. So there were obviously other initiatives than the CAMAS data set, and I just would like to briefly highlight two data products that were released recently. One of them is HySets, and HySets is a really massive data set that covers North America and provides daily data for about 14,000 watersheds in North America. Another really important data set is GSIM, and GSIM was produced by Addor and Lucas Gudmundsson. And the coverage is huge, many gauges are involved, but it's very important to keep in mind that they only distribute flow indices and no time series, unlike the other datasets I've mentioned so far. They've done an amazing job quality controlling the data, and if you're interested in how it can be done, do check their paper. So looking back a little bit, how much progress have we achieved over the last few years? A lot of new data has been released and has been taken up in academia, but also in the industry. We've established new standards to share hydrological data, which means that these datasets are fairly comparable and can be used together in large-scale studies. There have been benefits in two fields, I would argue. I mean, one of them is modeling. These data sets have really facilitated the benchmarking of models, of rainfall runoff models. And also they've literally enabled the emergence of machine learning models for hydrology. And in terms of process understanding, I think these new data have really provided new insights into hydrological processes. And here is just one example. It's a study that was published recently in Nature Communications, and that is based on CAMELS Brazil, the flow data from CAMELS Brazil. And here you're looking at different stream flow trends. And because so many catchments were included in CAMELS Brazil, it became possible to look at the spatial patterns of these different trends and to differentiate between accelerating, waiting, drying, and decelerating trend. So it's really something that was enabled by one of these large sample hydrology datasets. But I really think we should not be too complacent and also be quite critical and think about things we could do better. Currently, there isn't global data sets that is publicly available and that provides daily stream flow time series and catchment attributes. The comparability of the different data sets remains limited, as I mentioned, often because national data sets were used and qualitative classes make comparison difficult. And finally, and that's something that is really important to stress, and it is that creating and maintaining a large sample hydrology dataset requires a lot of work. So I've been involved in many of these projects, and typically, and I've tried with other people behind the dataset to estimate how long it takes to produce one of these datasets. And we've estimated that it takes somewhere between 1 and 2 years full time to produce one of these datasets. So it's way more work than what people think at the beginning. And this is because it's a lot of data to process, and then it also takes a lot of time to solve license issues. So we sat down and discussed what we could do about these different issues, and we wrote a paper about it. And an idea we had was, well, would make sense to move the production of the dataset to the cloud. And the idea was to have an online platform to produce these datasets with minimum data and minimum effort. And the basic idea would be to enable users to upload catchment boundaries as shapefiles and flow data, and to intersect these shapefiles with the grids that contain attributes in atmospheric forcing completely online. And to a great extent, it would help us to address and actually even solve, in some cases, these three challenges. It would make creating data sets much, much easier. It would lower the bar, meaning that people who have data to share but don't have the time to create a whole large topography data set can actually still release their data together with atmospheric forcing and catchment attributes. It would mean that the comparability of the different data sets is much increased because all the attributes will be derived from the same data sets. I mean, we might have different independent national data sets, but they would all rely on the same global data set for the attributes and time series. So it will increase the comparability. And the vision really was to create a community data set at the global scale that people could contribute to. And it's one of these things that might sound easy, but actually took a lot of time to make happen. But yeah, I'm quite pleased to say that it is something that is now operational. And it is part of a project that we've called Caravan. And as you might guess from the name Caravan, Caravan aims to bring together large topography data sets. Many of them are canvas data sets. And on top of being a global data set itself, it's also an online platform for people to generate large topography data set. And this initiative is really a collaboration between industry and academia. And Frédéric Kratzert, who is here in picture, is really leading the development and the deployment of Caravan. And I think Frédéric, is in the audience and will be there to answer questions if you have questions on Caravan. So let me tell you a little bit more about Caravan and how it works and what we're trying to achieve with it. So Caravan has two parts. It's an online platform and it's a data set. So let me tell you about the online platform first. The online platform is a platform onto which you can upload shapefiles and flow data, and where atmospheric forcing and attributes will be retrieved from Era 5 land for the atmospheric forcing. And Era 5 land is a reanalysis that many of you will be familiar with, a reanalysis produced by ECMWF, and from which we extract a range of atmospheric variables, including temperature and precipitation, but also some land surface variables like soil moisture and snow water equivalent. And for the attributes, we use the global dataset Hydro Atlas, which is part of the HydroSheds family of products that is created by Bernard Leonard and his team at the University of McGill in Canada. And Caravan is based on Google Earth Engine, which means that all the data processing occurs on Google Earth Engine. And so for Canals US, for instance, I had to download all the data sources. But in this case, you don't even have to download Era 5 land, or you don't have to download Hydro Atlas. There are all data sets that are available online already that we clip on the cloud using Google Earth Engine. And the code is there for everybody to use for any given basin. These data sets are global data sets, so any basin on land is covered by these two data sets and can be uploaded, and attributes and forcing can be retrieved. And for this, we use Jupyter notebooks. So this was the platform. Let me tell you about the dataset component of Caravan. So for dataset component, we've brought together datasets that include daily stream flow time series and that have a permissive license that enables us to redistribute the flow data. Here's a list of the datasets. Many catchments come from high sets. Actually, about 2/3 of the catchments come from high sets, and the different command sets are used, and Lama is also used, and Lama covers the Danube basin. So in total, we have about almost actually 7,000 catchments in the Caravan dataset. And here is a plot showing you the length of the record that we have for these catchments. And you can see that for a very large majority of the catchments, we have relatively long time series, 25, 30, 35 years of data, which is really important when interested in changes, when we try to assess trends, and also when we're interested in extreme events, because obviously the longer the time series, the more extreme events will be covered by these time series. Now, if we go back to this map, you'd say, well, the spatial coverage is not great, is it? And I guess it would be right. But what if we looked at it not in a that long space, but if we looked at it from a climate zone kind of perspective? Here's what you get. Here we're using the GENS climate zones. GENS stands for Global Environmental Stratifications. And on your screen, they ranked from left to right, from very, very cold to very, very hot to the right. In the bottom part of the plot, you see the fraction of the global landmass. And on the top half of the plot, you see what we cover in Caravan. And you see that the fraction of the global landmass and what we cover in Caravan actually correspond fairly well. And this is really encouraging. But obviously, climate zones don't tell the whole stories. You definitely can have two catchments in the same climate zone that behave very differently. So we need actually more data to complement the dataset that we currently have. And the vision is really to create a growing community dataset to facilitate data sharing and collaborations. And so let me just walk you through how you could actually contribute to Caravan and use the online platform to create an extension. So we created a wiki, and there are three main steps that you can follow if you want to extend Caravan with new catchments. So the first step here is the extraction of time series and attributes. So what it takes is shapefile of the catchment boundaries that you can upload to Earth Engine. And there is really a step-by-step tutorial in this wiki that tells you how to do it so that you don't have to do any local computation. All the computation is done in the cloud, and you don't have to do any coding, right? And the coding has been done already. And what you get from this first step is two things. First, time series, and the other one is a set of catchment attributes derived from HydroAtlas. And if you want to access the wiki, the link is at the bottom of this screen. So this was a first step. The second step is all about merging the data that you've just extracted from Earth Engine with Streamflow. And this involves you downloading the data from Earth Engine and merging the data with your Streamflow data that you have locally on your computer. And this is where the license is defined. And obviously, this is something that you have to agree on beforehand with the owner of the data. Often it's a public entity. What we hope is that people will select licenses that are open, that will let others use the data. But if you decided, for instance, that you didn't want the data to be used for commercial purposes, it's obviously an option. So the second step enables you to format the data so that it can be combined with the rest of Caravan, so that the format is the same as the format that we use for the other regions of Caravan. And the result is basically a Caravan extension for your regions, for the watersheds that you've provided shapefiles for. And finally, once you have this, well, you might as well decide to share the data, and that's the third step. And this involves uploading the data. I mean, we're using Zenodo to do this, but obviously there are other data portals that can be used. And this lets you share data online with the community. And this gives you a publicly available Caravan extension with a license attribution that you have picked. And again, the link to do this, to let the community know that you've produced an extension, is provided here at the bottom of the screen. So to wrap up, let me just give you an example. This is an extension of Caravan for Denmark. So Julian Koch used the online Caravan platform to extract time series and attribute for 308 catchments in Denmark, and chose a Creative Commons Attribution 4.0 international license, and uploaded the data onto Zenodo. And the link to download the data is there. And we were very pleased actually when this happened, and we're hoping that there'll be other extension of Canons. I just wanted to give a shout out to this initiative, which I find it very exciting. It's an initiative called Robin. And Robin aims to better assess the impacts of climate change on flow. And for this, they're looking for partners to provide flow data, specifically from catchment with little to no human interventions. And they have already a fairly large network of partners, as you can see from this map. There are quite a few prospective partners too, but they're looking for more partners for this project. We are in touch with them to use Caravan to extract attributes and time series for their catchment, because their focus is really on flow. If you're interested in this project and want to know more about it, I recommend that you contact Jamie Hannaford, who is the PI at UKCH. And I'll just finish with just one slide on what you can do. But well, first, as you've seen, there are many large sample data sets that are available. You might want to give them a try. They're actually quite fun to work with. You can become an advocate of open data. You can become an actor of data release. There are many things you can do. You can share your data. You can create your own data set, or you can decide to join Robin, or you can decide to create a Caravan extension. You can evaluate the Caravan data and compare it with national data sets, because comparing global and national data sets will reveal how uncertain data are, and quantifying uncertainty is something we want to become better at in large sample hydrology. It will also be essential to better determine what the information content of these different data sets are, how good global data sets are. And you can also add attributes when you use Google Earth Engine, because Google Earth Engine has a very large catalog of data sets. And so you can extract attributes from other catalogs than for other data sets than HydroAtlas. And you might ask, well, why does it matter? Well, really, open large sample data sets are completely essential to advance hydrological science. They're really important for us to better understand hydrological processes, to better identify the impacts of climate change on flow, to produce better models, and also to produce better forecasts. The more data is available in a region, the better the forecast for this region will be. This initiative is also a way for agencies to reach the open data goals and to improve the accessibility of their data. And there has been already quite a few public entities that have decided to contribute to, for instance, a Canon Data Set to release their data because of the audience that they can reach most immediately by releasing the data this way. And that's what we're trying to do with Caravan too. We try to maximize the audience that can be reached, and at the same time, minimize the workload for whoever decides to produce an extension and contribute to Caravan, to make it easier and to lower the bar and to facilitate and accelerate data sharing in hydrology. And also for you as a user, if you use Caravan, you get a data set that enables you to compare your catchment to thousands of other catchments worldwide. So giving you a big picture of what's going on. So I hope this resonates with you. And with this, I would like to thank you for your attention, and I'd be happy to take questions.